So I was asking, how do we calculate for the coefficient of friction? Okay. Now, when we look at the horizontal analysis of the body equilibrium. Yes, horizontally, the body is in equilibrium because it is moving with a constant velocity. So dynamic equilibrium. If dynamic equilibrium, then the force at this side, at the right-hand side, okay, force at right-hand side must be equal to the force at the left-hand side, so that we have a state of equilibrium. Okay. Hello?
Mr. Yeah. Please,
Oh,
it's
please.
breaking.
I am coming. It will stabilize soon. Hello. Hello? Hello? Anita? I'm Mr. Kora. Hello? Hello? Can you hear me now?
Yes.
My bro. Okay. Okay, so what I'm saying is that because the body is moving at a constant velocity, meaning we have a situation of dynamic equilibrium. So the right-hand side force must be equal to the left-hand side force. What we have here, we have the force with which your younger brother pulls the mass with. What we have at the left-hand side, yes, what we have here, what we have here.
Sir, please, the line is breaking.
Hello? Hello? Can you hear? Hello? I hope you can hear me. Where are they?
Sir, please, the line is breaking.
Shit. Okay. But is it better? Is it better?
Yes.
It's getting better.
Okay, then it has to get better. So I'll send the recording. So you let's manage. Okay, it's not my fault. So we have frictional force at the opposite end. You see, what is friction? Frictional force opposes motion. Opposes motion. So for frictional force, its work is always to oppose motion. So when you are moving in this direction, frictional force would act in the opposite direction. So you are moving in this direction, friction is there to oppose you, so it will be in the opposite direction. If you are moving in this direction, friction will act in this direction. So if the body is being put horizontally in this direction, then oppositely there will be frictional force, friction. Please, are we okay? Are we okay?
Yes, please.
Good. So horizontal equilibrium, we expect a force of 140 Newton to be balanced by friction, frictional force, because we have a state of dynamic equilibrium. Now, how do we calculate friction? Frictional force is equal to the coefficient of friction times the reactional force, R. The coefficient of frictional force, okay, is a quality, or yes, a quality of the surface on which the body moves. If the surface is too rough, the value of mu, coefficient of friction, is high. If the surface is too smooth, the value of coefficient of friction is too low. But coefficient of friction mu is between 0 to 1. If mu is equal to 1, then it means the surface is too rough surface. If the value is equal to 0, then so smooth. The surface is so smooth, so frictional force is so low, right? So frictional force is given by the nature of the surface, mu, times reactional force, R. And how did we calculate for the reaction here? This reaction, we say, is balanced by the weight. So R is equal to mg. R is equal to mg. Therefore, if R is equal to the, mg, then frictional force is equal to coefficient of friction times mass times gravity, because R is equal to mg. Please, are we okay? Are we fine? Are they there? Or the network has taken them away? Sanam, Akwavala, Adoyabwa. So we have 140 being equal to friction, which is mu mg. We already have calculated mg. I've just come. Okay. So as for the network, let's manage, okay? All right. So because horizontal, this is equal to this. 140 Newton is equal to mu, which we are looking for, times mg. What is mg? Mg is 200. Therefore, mu is equal to 140 divided by 200. And what is 14 over 20? 7 on 5. Sorry, 7 on 10. 7 on 10. So we have 0.7 as the coefficient of friction. Please, are we fine? Are we fine?
Yes.
Sir, please, does it have a unit?
No, it's non-dimensional. It has no.
Mr. Dia.
Hello.
So you're basically saying that mu is equal to force over reaction.
Frictional force. Frictional force F is equal to mu times the reactional force. So this is the reactional force. So we could still break it as mu times mass times gravity, because for a body that is lying flat on the ground, the weight is equal to the reaction. So this is for this context or situation. In some other situation, we'll have a different expression for the reactional force. Is that okay? So you take this for now, but friction is equal, frictional force given by the coefficient of friction times the reaction. All right. All right.
Mr. Dia, please, your line was breaking.
Eliana, yes, frictional force is equal to this, mu times R. But in some situation, R will change. R is not always equal to mg. In some other.
This is still breaking.
You agree? Eh? I'll send the video, so please manage me, okay? Okay, so this is it. Question 2. Question 2. We'll start inclined plane, and under inclined plane, reaction is different. So that's why I'm saying R is equal to mg for this situation. A person of mass 45 kilograms is in a lift. And this is a lift. I have Adwa, are you there? So Adwa's weight or mass is given by 45. The lift is going vertically upward with a constant velocity. So the lift is going vertically upwards with a constant velocity. And once it is at a constant velocity, it means that we have a situation of dynamic equilibrium. Please, are we fine?
Yes.
Okay.
Yes, please.
So we have a dynamic equilibrium. Now, it also means that there is no acceleration on the body. So it implies that the net force is equal to 0. If the net force is equal to 0, then the weight of the body must balance the reaction, because the net force is 0. So it means that the reactional force, which would occur in the opposite direction, is balanced by the weight of the person. Weight. So we have mass 45 kilogram times the acceleration due to gravity, which is 450 Newton. So this is the reactional force. Now, if the body is not at constant velocity, but accelerating, the body is accelerating. Okay, if we don't have this situation and we have an accelerating body, how can we determine the reactional force? It means that once the body accelerates, it means that there will be a certain force over here, which will be given by the mass of this lift times the acceleration with which it moves. Okay, if the body is not accelerating, then the force here will be given by the mass, okay, times the acceleration of the body. In that case, the net force would be equal to M times A minus the weight, M times G. Okay, therefore the net force will be given by M out A minus G. And the net force will certainly be the reactional force. The reactional force would have been A minus G. If the body is said to be accelerating, please, are we okay? Are we fine? Okay. Another question. I'm dictating another question, so please pay attention and listen. Do I
Mr.
start?
Dia, please, I'm not done writing.
Okay, then hurry up. Do I start? Hello?
Please, I'm almost done.
Okay.
Please.
Okay. All right. So, okay, let me take a shot and send it into the group so you could pick it from there. All right.
Yes, please.
Okay, so I've sent it into the group. Have you seen it? Hello?
No, please.
Oh. I just sent it to him.
It's only the old questions that are there.
Check. Check.
Please, I've seen it now.
Okay, so
Thank
please look at it, go through or copy so we can solve it together. So it says one end of a light inextensible string is attached to a horizontal ceiling. Don't let the question scare you. It's not difficult, okay? That's why I'm here. So we will all look at it. So one end of a light inextensible string is attached to a horizontal ceiling. And a particle of 4 kg is attached to the other end of the string. The particle is pulled sideways. The particle is pulled sideways by a horizontal force of 20 Newton until the equilibrium position is reached. Find the tension in the string T and the angle theta which the string makes with the vertical into bracket in the equilibrium position. So please try drawing it first thing. Try drawing it, okay? Then we look at it. One end of a light inextensible string. What it means is that the string doesn't stretch, cannot be extended. It's not that elastic type of string. Please, are you with me? So it's attached to a horizontal ceiling. The ceiling is horizontal. So draw a horizontal line with a ciliated marks behind it to represent the ceiling. Are you with me? And a particle of 4 kg is attached to one end of the string. So the particle is pulled sideways by a horizontal force of 20 Newton. Okay. All right, so let's look at how the drawing will be. So first, I have a horizontal ceiling. So this is my ceiling. This is my ceiling. We have an inextensible string. An inextensible string, okay, at an angle to the ceiling. You see, if I draw a vertical line, this is the angle the string makes with the ceiling. Now at the other end of it, there is a mass. This mass that is being pulled by a force. So we are told that a force, the mass is 4 kilograms. This is being pulled horizontally, pulled sideways by a horizontal force of 20 Newton. So the mass is being pulled by a horizontal force of 20 Newton until equilibrium position is attained. Find the tension in the string. So there's the string. There's the string. There's the mass. It's being pulled by this force. We are asked to find the tension in the string, T, and the angle theta, which the string makes with the vertical. So this is the imaginary vertical, okay, and the angle the string makes with it is theta. So we are looking for this tension in the string T and then the angle the string makes with the vertical. Please, are we fine with the diagram? Are we fine with the diagram?
Yes.
Okay. Now, our big challenge is how do we determine the tension and the angle? Okay. This, we are told from the question that it was pulled till equilibrium is attained. Equilibrium is attained. So it means it was pulled till the net force acting on the body from all angles is equal to 0. So let's resolve this. Let's resolve the tension. We have the angle and then the tension. Let's resolve to get a vertical component of this. Okay, a vertical component of it, and then a horizontal component of the tension. So we are resolving to obtain this part. Okay, certainly this becomes, will this side become the horizontal or the adjacent? This side, will it become the horizontal or the adjacent? Yes. This side, will it, when we resolve with the angle and then the tension, will this side become the horizontal or the adjacent?
Adjacent.
Good, because this side is adjacent to the angle. So help me resolve this side with respect to the angle and then the tension. How do we do that? Or do it and tell me what the adjacent would be. We've done resolution of forces, so please do it. If you are done, what did you get for the adjacent? Hello, what did you get for this side? Resolution of this side. Hey, nobody is talking. Oh, Adwa, Eliana, Akofala, Sanam, Adwa, Yabua. Okay, this side becomes T cos theta. And then this side.
T cos theta.
Good. And then this side becomes T sine theta. Okay. Now, instead of having the adjacent here, let's bring it on the mass, equal vectors. Okay. So instead of having this side here, it's the same as bringing it here. T cos theta is here. Are we fine? Don't forget, you can understand this from this angle alternates with this angle. So if this is theta, this will also be theta. So you can bring the angle here and so resolve, and it will be the same. Are we fine? Are we okay? Now, once the body is in equilibrium, okay, when we look at vertical equilibrium, it means once the body is in equilibrium, it means all right. Okay. So once the body is in equilibrium, if we look at a vertical Mirabel, just recording that.
Hello.
And today I'm suffering. The network is beating me. Oh. Okay. So when we look at vertical equilibrium, it means T cos theta is equal to the weight of the mass, which is mg. This is equation 1. When we look at horizontal equilibrium, it means T sine theta must be balanced by the horizontal force pulling the mass, 20 Newton. Equation 2. Okay. Now, T cos theta would be equal to 4 times acceleration due to gravity, which is 40. So we have T cos theta giving us that, and then T sine theta is also giving us 20. So this is 40, this is 20. Are we okay? Look at it, and then if you have any concern, let me know. So let me modify something. T cos theta is equal to mg is the vertical equilibrium. Then horizontal equilibrium we have T sine theta equal to 20. Are we fine with what I've done so far?
Yes.
Good. Now, this is 1, this is 2. Divide equation 1 by equation 2. Divide.
Mr. Dua,
Hello.
please, why did you equate it to mg?
We are looking at, we are told the body is in equilibrium, meaning that the net forces in all directions, horizontal, vertical, must be equal to what? Must be equal to what? 0. So it means that when we look at vertical analysis, T cos theta must balance the weights, mg. Vertical analysis. Horizontal analysis, T sine theta must be equal to the horizontal force pulling it. That's it. Are you okay? That was
Yes, please.
good. So divide 1 by 2. When we divide equation 1 by 2, we have T sine theta over T cos theta, giving us 20 on 40. And what is sine theta over cos theta?
Tan theta.
Oh, so we have tan theta equal to 0.5. Of course, 2 on 4 is 1 on 2. So 0.5. Therefore, we can find theta straight away. Theta is therefore equal to tan inverse of 0.5. And what is tan? What is theta? What is theta? Hey, what is theta? Our network is not good.
26.57, okay, 27 degrees.